References and bias currents. Today we're going to go through a few circuits for how we generate a constant voltage and can generate a constant current on a chip. Because on the integrated circuit, we do need something like a reference, a fixed point in voltage or current that we can kind of hold on to, that we can use as the comparison for our analog to digital converters. We can figure out, well, what a voltage should be when we take in the 3.6 to 4.3 volt from the lithium ion battery, and we want to make sure that we actually generate exactly 1.2 volt for our digital core. But how do we know what 1.2 volt is? Or indeed, when you charge a lithium ion battery, how do you know that you do not ever exceed the maximum voltage on the lithium ion battery? So some of them, for example, if you go above 4.3 volt, then bad things can happen. So that's the topic for today. We want to understand why we need references and bias currents, and also introduce some of the more common topologies for integrated circuits. So when you first start out in integrated circuits, and then in your schematics, in your test bench, in your SPICE simulation, you will use these two symbols, a voltage source and a current source. The voltage source is, well, you can just put in the voltage and it will always force that voltage. It has what we call zero source impedance. It doesn't care what the circuit is. If you say it's going to be 0.5 volt, then it's going to force 0.5 volt. And currents are the same. Current sources are the same. It's just different, right? So if you say that the current coming out of this current source is, let's pick a number, 1 milliamp, then it will push 1 milliamp into your SPICE circuit no matter what happens. So even if your transistor happens to be turned off, well, the current source doesn't care. It'll still push 1 milliamp. So these type of sources, now current source, are recognized by that fact that they can push a current, and they have what's called infinite output impedance. They do not care about the resistance in the node. They will push, well, the voltage really. They will push a current independent of voltage. But these two ideal current sources do not exist on our chip. We cannot tape them out, right? We have to actually make the circuit. We have to make the circuit real. Now, one thing that I want to touch on before we proceed with references of bias, and that is that even though we can generate a voltage, in this case VR, internally on the chip, then there is still a challenge of distributing that voltage, because as you know, a voltage is really only defined between 2 points. It's not defined in a node. There is no such thing as the voltage in a node. What we mean by that is always the voltage in this particular node referred to ground is 1.2 volt. But the ground might not be the same. So if I have on the one side of the chip my reference, and on the other side I have the analog to digital converter, that where you want to use the reference. If there's some distance there, well, there's some resistance in the ground. So you can think about it like we have a impedance from the local ground, you can see my pointer now, all the way down to the actual ground, whatever that is. So, and that impedance might be dependent on time, it might depend on voltage, it might depend on frequency. Well, it might not just be a resistor. You can actually have an inductor here, and you can have had induced voltage in that, or induced current really, and that impedance. It could be dependent on temperature. It could be dependent on process, it could depend on a lot of things. So if I now start with my node where I know I have 1.2 volt locally, and I distribute that on a wire across the chip, then the wire will have resistance. And when I get to my destination, well, if there's no current flowing in the wire at all, no current, then at the destination, the plus sign here, well, that will be at the same voltage or same potential referred to the local ground, well, here at the source, as it is at the source. But the local ground might not be the same because it might have a different impedance. Now, usually wires that we have on the chip, they don't really have any resistance to ground. Well, like they do, but it's so really, really large that we don't care. But they do have capacitance. They do have a capacitance to ground, so there's also a time dependence in a wire. By the way, a good way to model a wire is 2 capacitors to ground and resistance between. That's a common model used for digital circuits, wire delay. You have 2 capacitors to ground, and there's a resistor in between. And you split the capacitance of the wire into 2, and that kind of works for sort of simple models. Anyway, that means that if I want a robust reference, then I don't really want to distribute voltage across the chip, because I can't rely on the ground being the same, especially because, for example, in a step-down converter going from 3.6 volts down to 1.2 volts, and we use a DC-DC or a buck regulator, then the buck regulators, they are PWM based. Well, not PWM necessarily, but at least they have a switching node. And that has a tendency to pump currents into ground. So that ground locally will bounce up and down. Now, definitely you don't have necessarily the same voltage, and you actually also have a potential for noise injection into your reference. So that means if you actually want to distribute references on a chip, quite often it's better to do it in the current domain. So what we can do is that we can convert our known reference voltage into a current locally. Now, the current, well, yes, that will flow through the ground impedance, but the current, as long as we don't lose any current in the wire from the source to the destination, and we basically put a resistor between the 2 wires here, then we can actually know the current in that resistor. Because currents flow in the loop. We know that as long as it doesn't disappear anyway, as long as there's only one loop, then we know that the current will be the same. So, for example, if I actually have a voltage divided by a resistor, and I use exactly the same resistor on the other side, now I know my voltage is the same. My reference voltage has been copied all across the chip, and I'm happy. However, we can't make resistors that precise. Usually, cross-die variation might be a few %. So there are limits to how precise we can make voltage references or distribute voltage references with the method that I'm showing you right now. So if you actually want something ultra precise, like what you need for a battery charger in a lithium-ion battery charger where you have to terminate within the voltage within 1% or something like that, otherwise things go wrong, then you cannot use currents as sort of your distribution method. Then you have to use the voltage. But now we're back to sort of a catch-22. I said that in order to distribute voltages accurately across the chip, we should do it in the current domain. But now I'm saying, well, don't do it in the current domain because you can only get plus minus 2% accuracy. You should do it in the voltage domain. So these two things sound like they can't both be true, but the thing is, if you actually need a precise voltage reference in a battery charger, then you have to distribute the current, but then the wire cannot really be there. You can't do it across the chip. You need your bandgap or your voltage reference circuit to be right next to where you need it. That's the only way to make it really precise and get that 0.5% or even better. So know that what we're going to look at now is how to generate these currents and voltages. But know that just distributing them across the chip can be a tricky thing and something you actually have to think about. Details matter. The traditional way to make a voltage reference, and in my opinion, the best way to do it, is what is called a bandgap reference. The bandgap reference relies on the forward diode. We could either use a bipolar transistor in a diode connection like this. It's not ideal because then you have the base current, and also the base current these days, if you're going to do low power design, the base current is actually could be a significant portion of your total current. So you can use just a diode junction. Quite often in references you'll see later, well actually no, if you look in papers you will see that quite often it's a vertical PNP device where you use only the base-emitter. Yeah, base-emitter junction as your diode. But the physics is pretty much the same. So we have some sort of scale current. When we look at the current in this system, we have a voltage from the base to the emitter. We have, well, we know that there's some leakage current when you flip the device in reverse biased. There's some base current, but let's assume that we can ignore the base current for now. Then we're left with a exponential relationship between the current and the voltage across the device. Now we can flip that around and we can see that we have a base-emitter voltage that is proportional to KT divided by Q, so the thermal voltage, about 26 millivolts at the room temperature, and then a logarithm over a fraction where you have the collector current on top and you have the scale current at the bottom. Now, if you've never seen this equation before and I ask, what is the temperature dependence of the base-emitter voltage, it would be natural to say it's proportional to temperature, because we can see the temperature here. However, it isn't. It's actually inversely proportional to temperature. And the reason for that is hidden in the IS, the scale current. So if we write out the scale current, then we have the charge of the electron, we have the area of the, well, junction. We have the intrinsic carrier concentration squared. And then we have a factor that is dependent on the diffusion constant of electrons divided by the diffusion length of electrons divided by the acceptor concentration. So the two factors in the parentheses, I'm actually not sure about the temperature dependence on these two factors. But what is very clear is that the intrinsic carrier concentration, that has a tremendous increase with temperature. So I'm not going to go through the details for the calculation. Actually, maybe I should bring it up. So I wrote this, I started digging down into why does it really have this negative temperature coefficient? And it's kind of fun. I'm not going to go through the details, but you can go through, let's see, let me switch the screens here. You can go to the lecture notes and you will find diodes, and you can go in and you can, well, I talk about the intrinsic carrier concentration, how it is a factor. Let's make it bigger. It's a factor that depends on the square root of what's called the density of states in the conduction band and the valence band. And then it depends on the bandgap of silicon. Now, the density of states, that is given by this equation. Now, this may look, it's not really complicated. There's not that many factors. I mean, it's let's see, you have 2, you have pi, you have k, and you have t. Those should be known. You have Planck's constants. And then you have the more fuzzy thing that is called the mass of electrons. And this has the power of 3 to 2. So you can see that there is a temperature dependence both in the exponential factor up here and also in the density of states. Now, I go through in this diode thing how it's possible, or actually how they go from all the way from Schrödinger, the three-dimensional equation for Schrödinger and the density of states, or compute the density of states from Schrödinger. So you start with Schrödinger, you go via the momentum space, and then you do use the this is the band structure to convert to energy, and then you have the bending of this is the curvature of the band structure, which is the effective mass of the electrons, and then you sort of compute these things, and you use the Fermi-Dirac or the Fermi equation to give you the number of carriers as a function of this vector first here, which is the sort of based on the three-dimensional Schrödinger equation and the density of states, and so on. I'm not a quantum physicist. I couldn't do this I can follow the arguments, but I can't really do it from first principles. But I think it's important to know that underlying here, when we're talking about polars and these type of devices, we're talking quantum mechanics. And you can go through all the equations and you can sort of separate out what's proportional to temperature, or what's dependent on temperature and what's not dependent on temperature. And you're left with an equation where you have the base emitter voltage is equal to the thermal voltage times some sort of factor. The factor is written down here. That is not temperature dependent. Minus 3 times the ln of T plus the bandgap voltage. Now, what we can immediately observe is that if we set the temperature to 0, so absolute 0, as in 0 Kelvin, then the first factor in this equation disappears, and we're left with that the base emitter voltage actually is equal to the bandgap of silicon. This is why we call these circuits bandgap references, because they depend on the bandgap of silicon, which is 1.12 volts, electron volts. Now, at 0, it doesn't really, I don't think the bandgap, I don't think you actually have, I don't think the base emitter junction necessarily works, but anyway, that's where it extrapolates to. And all the base emitter junction in the world at 0 Kelvin go to roughly the bandgap of silicon. Okay, now it's not obvious, at least to me it's not obvious, why the first factor in this equation actually has a negative temperature coefficient, but it does. So if you plot it in Python, for example, you will see that the diode voltage, well, it starts at the bandgap of silicon, and then it goes down. And the linearity of this curve is actually quite good. If we plot the error versus a linear curve, we can see actually it has this second order type of function. So a few plus minus a few millivolts across the band from minus 25 to 125 degrees. And now we're talking, right? Because now we have a pretty precise relationship between temperature and voltage. We know that there is an inverse relation, so that as temperature increases, the base emitter voltage and the diode voltage will reduce. So we don't have a constant voltage yet, but maybe we could generate a constant voltage using this feature. Well, what we would need was something that has the inverse relationship, so it actually increases with temperature. And that's where we get to the bandgap references. So setup is this circuit. Assume we put current into a diode of size 1, and we'll get a certain voltage across the diode. We can copy that voltage to another place using an op-amp. So in this case, the current in this current mirror is the same on both sides. Now, if we make the second diode here n times larger, then well, it should be intuitive that the voltage on that diode is going to be lower because now our area is larger. So remember in the scale current we had the area, well, now it's going to be lower. So even if we match these two diodes exactly in terms of doping and all the details of the quantum mechanical details, direction, orientation, and so on, then the voltage is still going to be lower. What's interesting is that if we then have a resistor in between, and we copy the voltage, as I said, with the op-amp, we know that at the top of the resistor, we have the first diode voltage. At the bottom of the resistor, we have the second diode voltage. So if we subtract those two, and then put in the equation for the diode voltages, so that's the thermal voltage, it's the ln of ID divided by IS. And now, we know that the currents in the two, if the current mirror is matched exactly, then the currents are the same, and the ln of ID, that disappears. And we're left with a relationship between the two scale currents. Now, as I said, if we have the same orientation, we have the same doping, then the only difference between these two diodes is the area. And now we can actually just plug in the scale current. We can take it out. So everything but the size difference disappear. And now we're left with a relationship where the difference between the two diode voltages is given by the thermal voltage times a logarithm of a size difference. And this is definitely proportional to temperature, right? Because ln of n, that's just given by the size difference between the diodes. And the thermal voltage, kT divided by Q, well, there's only one temperature in there. So, we placed a voltage across the resistor that is proportional to temperature. Now, the neat thing about this feedback circuit with the op-amp is that since we know, well, if we assume, I should say, that the VD1 and the VR1 are the same, and the op-amp and the current mirror is doing its job, then we know we have this delta diode voltage across the R1 resistor, and we know ID, because it'll just be VT, thermal voltage, ln n, divided by R1. Cool. I think it's cool. Now, there's a bunch of assumptions we made. We said, okay, if the op-amp copies the voltage precisely, if the currents are the same, if the diodes are matched. So there are a lot of assumptions that make this relationship true. And those assumptions are, of course, what is difficult to get right. It's not possible to have exactly the same voltage on both sides here. There will always be some remaining offset from the op-amp. The current mirrors, the transistors in the current mirror, will not match precisely. There will be matching issues there. There are techniques to address it, like dynamic element matching and so on. The output impedance of the current mirror will matter because, well, the voltage should be in the same on both sides, so maybe it's not a big deal, but it will contribute, I think. So there are a lot of assumptions and circuit challenges that can make this not precise. But that's why we learn to be analog engineers, right? We're sort of here to solve problems like that. But the principle is there. So now we're left with the problem of how do we combine the negative voltage coefficient with regards to temperature of the diode voltage with this positive temperature coefficient across this resistor. So there's a number of ways to do it. In this case, the current that will flow in the transistors, that's proportional to temperature because the voltage across this resistor is proportional to temperature. So what we could do is we could just put that current into a diode. Now, the diode doesn't really change. The diode voltage, it's not that dependent on current. A little bit. It is. But even though the current is proportional to temperature, that doesn't change the current a whole. That doesn't change this VD3 a whole lot because there's an exponential relationship between the diode voltage and current. So a small change in current doesn't give you a large change in the diode voltage. And now we know that we have a negative temperature coefficient on the VD3. So if I place on top a resistor, that is going to be, this R2 resistor is going to be a lot larger than the R1, because I have to take that small difference. Oh, maybe I should point that out. ln of 8 is about 2. So if you have 1 to 8 size difference, you have 2 times the thermal voltage. And the thermal voltage at room temperature is about 26 millivolts. So you're going to get, what's that? 52 millivolts. That's the delta VBE. The diode voltage usually is on the order of maybe half a volt. So probably between R1 and R2, you're going to have a size difference of about maybe 10 or 11 or something like that. The exact values you have to actually simulate, or you can compute an initial guess, but you need to simulate it. But if you tune R2 correctly, you can get to the point where as temperature increases, well, the VD3 decreases, but the voltage across R2 increases, and you're left with a reference that is stable. It'll have the second order gradient, and it might, well, it'd be like this. Let's see, like that. And it might tilt a bit depending on corners, but it can be extremely precise. Cool, right? There are many ways to combine these two voltages. If you have a lot of headroom, if you're running at 3 volt, for example, or actually both of these can run, both of these need about 1.5 volt to operate, because you can actually see that because the reference voltage here, that's going to be pretty close to a bit higher than the bandgap voltage, around 1.2 volts. And that's just inherent in this structure. In the case of here, we'll have the voltage there, we'll have 1.2 volt coming out, so it's roughly the same thing. Here we're just stacking it. We're basically doing exactly the same. We're reusing the fact that we have VD1 at this point, and that's going to decrease with temperature. And then we place a delta across the R2 that increases with temperature, and the reference will be constant. So that's one way to do it. There are many of these ways, and what I would recommend is that you find a paper in IEEE Explore, and you figure out how that works, and you'll see it's sort of, something like this. As long as you have high enough voltage, like 1.8 volt, then the band gaps that I'm showing you now are perfectly okay. Now, there's also one of the really, I guess, first implementations. Not the one you're looking at now, but the guy that this circuit is named after, the Brokaw reference. I think he was one of the pioneers within band gaps. I met him once, actually, at the ICCC. Anyway, that's neither here nor there. So, but I want to go through how the Brokaw reference works. It's actually the same principle. It just looks different. It looks complicated, maybe. So, first thing we need to realize is that the voltage across these two resistors is the same. So the plus and the minus point, the op-amp will force those two, or try to force those two voltages to be the same, which means that since the VDD is the same, then and R3 is equal to R4, then the voltage across the resistors are the same, and the currents must be the same. Now we have the bipolars. In this case, Q1 is larger than Q2. So it might be 1 to 8, or it might be a different relationship. From the VBG, we're dropping 1 base emitter voltage. So that means that we are here. There's going to be a difference in base emitter voltages across this R2. We can see that. So they have the same base, but since Q1 is bigger, then the emitter will be at a higher voltage. You need less base emitter voltage across Q1 than you do across Q2, since they have the same current but different area. That means that delta VBE will be across R2, and it's going to be the same situation as we had here back here. Oh, going back a bit, we're going to have across that R2 resistor VT ln times the size difference. That's going to be across this resistor. And that is actually going to set the current in this circuit. So at some point, then the op-amp will be happy because it's forced the two voltages at plus and minus to be the same. And when that happens, you have the delta VBE across R2, and the current in the Q1 branch is going to be the base emitter voltage divided by R2. Now we know it's the same current in Q2, and we can see those two currents are combined. Now it's just 2 times that current. The current's going to be proportional to absolute temperature. We're putting that into the R1 resistor, and now we have a voltage from the top of R1 to ground that increases with temperature. So if we look at VBG then, the output, then if we start, we go from ground, we go up over R1, that voltage is going to increase with temperature, and then we go a base emitter voltage up on Q2, and that voltage is going to decrease with temperature. And if you design it correct and get the resistors right, then the bandgap voltage is going to be constant with temperature. And we can see there's an equation here. We can see also that it looks similar to the equation I had earlier. We have at 0 temperature, 0 Kelvin, all these factors at the end disappear, and we're left with only the bandgap. At higher temperature, we have some sort of constant, -1, times the ln of the temperature. In this manner, it's actually written as a relationship between a T0 and a moving temperature, but that's okay. And then there is this factor that has the current densities of Q1 and Q2. It has the size differences between R2 and R1. And if you make this first factor in the parentheses the same as the bandgap voltage minus the VB0 divided by temperature, if you make those, or T0, that's 25 degrees or whatever, if you make the factors inside the parentheses disappear, then you're only left with this nonlinearity as a function of temperature. Cool, right? So same principle, just different circuit. So in these type of bandgap circuits, don't rely on your equations. Don't sit down and say, okay, the current in Q2 is given by IS times the exponential of the base emitter voltage, and then you try to work out all the equations and blah, 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 blah. Don't do that. Think. Before you do any equation, just think through it a bit, especially when it has op-amps, because you need to get that intuitive sense of what is actually happening in the circuit. Especially in these type of feedback loops, it can be tricky if you just start with pure equations and you try to sort of just power through. So think first, figure out how it works, and then you can write down the equations. So here's just an example of a Brokaw reference I designed a number of years ago. So we can see the output, the VBG, is around 1.2 volts, and it has this well-known bandgap shape. There are ways to compensate for that. There you can find sort of second-order compensation schemes in the literature. But one thing that will happen when you simulate different corners is that that curve will shift slightly. And so I haven't made a bandgap for a industrial integrated circuit, but I know quite a few designers that have made bandgaps, and it's quite rare to hit perfectly this curve. Quite often when we get it back from the foundry, it's tilted in one or the other direction. So getting that tuning right is quite tricky. Yeah, whether that's down to modeling or something, I don't know, but yeah, but usually we get it good enough. So one of the challenges with these sort of traditional bandgap circuits is that they require about 1.5 volts on the VDD. They can't operate lower than that, because if we go back to this circuit, let's take this one. So if we have 1.2 volt here, we need some voltage across the current mirror, because we need at least a saturation voltage in order to get the transistor into saturation. Unless you're operating in subthreshold, but for current mirrors, I'm not a big fan of subthreshold unless you have to. So about 1.5, maybe a bit lower. That's sort of the limit. But in modern technologies, if you don't have IO voltages, you only have the core voltage, like 0.8 volts, then it starts to become tricky. But actually, usually you have an IO voltage. Usually you have 1.8 volt. At least sort of in most, maybe it's older technologies, 22 nanometer and up. You'll have 1.8 volt. Probably lower down also, you have 1.8 volt. So you might not need a low voltage bandgap, but if you have to make a bandgap at around a volt or something like that, then the low power voltage bandgap is the way to go. So I'll try to explain how this works. So we start with our traditional bandgap circuit. The current in the transistors proportional to absolute temperature. If let's say I, for fun, add an op-amp, okay? A unity gain feedback op-amp. I copy the diode voltage to a output here. Though the output of the op-amp now will decrease with temperature, the voltage. So the voltage across R2 will decrease with temperature, right? Okay. That means that the current in the R2 will decrease with temperature, since the voltage across it decreases with temperature. Okay, what I want to try and convince you of is what you're looking at on the screen right now is exactly the same as the circuit. You don't need the op-amp. So what I've done now on both sides is to add a couple of more resistors. And the tricky thing, I think, to realize is that, yes, of course, the current in my current mirror now has changed, but still, there's going to be a delta voltage, a delta VD or a delta diode voltage across the R1. So across the R1 and the current in this diode on the left side and the right side, that's still going to be the same, and it's going to be proportional to absolute temperature. Sorry. That's just how it is. But the voltage across R2, both of those are given by the first diode, and that's decreasing with absolute temperature. Now we have a current going into the transistors. We have one that's proportional to absolute temperature and one that's inversely proportional to absolute temperature. And that's what I'm writing up here. The value, the current in the PMOS, you have one current that is VD divided by R2. And you have another, that's this delta VD divided by R1. And if you scale the resistors correctly, you can actually get a constant current. Now, if I have a constant current, I can just mirror that current, put that current into a resistor, and now I get a constant voltage. What you can see now is that the voltage at the output, well, that can be chosen freely. That can be half a volt, that can be whatever, because we can just size the R3 resistor. Another thing we can notice is that now the lowest possible operating temperature of our circuit is just given by a diode voltage, and then the saturation voltage of an NMOS. Oh, sorry, of a PMOS, or a PMOS cascade emitter, wherever the current mirror is. So we're now lowered it by about, let's say, at least 300 millivolts, maybe even more. So I think these type of low voltage bandgaps, we can get them down to maybe a volt, maybe even lower, but then it depends on how high does the diode voltage go at low temperature, right? Because at some point that might be a problem. I should also mention that resistors have a temperature coefficient. Depending on the type of doping on the polysilicon and the type of material, It can either have a positive or a negative temperature coefficient, but it does have a temperature coefficient. So for example, if you choose a P plus or P dot poly, then usually that has a positive temperature coefficient. But for this circuit, it doesn't matter that much, because it turns out that the output voltage, although it's a current into a resistor, if you put the equations up, you will figure out that the output voltage actually depends on relationships between resistors. And as long as all the resistors increase or decrease with the same type of coefficient, the relationship between them will stay the same. So that's usually not a problem. So the bandgap reference, you can read the original paper. It's not always that we need voltages, as I said in the beginning. Once we have a fixed voltage, which we now have, we quite often want to generate a current instead to be able to reliably distribute all across the chip. One way to do that is to use a voltage current converter. And what we're doing now is we're taking our fixed point in space, or in voltage rather, at the 1.2 volts, and we're copying that voltage across the resistor. Now, if we copy the voltage across the resistor, the current in this PMOS will be given by 1.2 volts divided by R. So that's going to be our output current, if we design the op-amp correctly and so on. And again, we don't need to put up equations for this circuit. We can simply realize that if we design it correctly, then the op-amp will force the two inputs, the plus and the minus, to be the same, which means that the voltage across the R here has to be 1.2 volt. Well, it doesn't have to be, but it should be. And then the current in the PMOS, well, that's going to be 1.2 volt divided by R. And what you should realize now is that if I have exactly the same resistor on the other side of the chip, I can just take a current, put it into that resistor, and the voltage across that resistor, as long as it's the same, will be 1.2 volts. I can freely choose what the voltage is going to be, determining on the size of the resistor that you use at the other end, but you see the point. This is a good way to distribute currents, bias currents, across the chip, or indeed reference currents for that matter. But sometimes we don't need all that precision. Actually, sometimes you don't want something that is stable. Sometimes you want parts of your circuit to have, or the current actually to have, maybe a positive temperature coefficient. One of the circuits that is quite often common to use for bias is what's called the GM cell, and that's what you're looking at now. There's a lot of equations, a lot of drawings. Okay, let's start first with a circuit understanding. Here at the top we have a PMOS current mirror. At the bottom here we have a NMOS current mirror. That just acts as a cascode, or not as a cascode, but as a voltage copier. So it'll take the voltage at the drain node and gate node of device 1 here and copy that to device 4. Actually, the 1 and 4 is the size difference. And then we have the NMOS at the bottom, where we have a 1 to 4 size difference. So if we do the same type of thinking, if we start at ground, we go up 1 VGS, we go down 1 VGS, we can see that the output voltage, that's going to be given by VGS1 minus VGS2, and then we can put in the values for the V effective and the threshold voltages, and we can figure out that it's going to be the difference between two threshold voltages. Now, this GM cell has a couple of stable operating points. So as long as there's some current flowing, then usually it will find a place where the feedback loop that is up here, controlling the current in the top, and the feedback loop down here finds a stable operating point. However, it's also possible for the current in this GM cell to be zero. If the current is zero everywhere, then the circuit also works while it's stable. That means that most actually references and bandgaps need some sort of startup circuit to get it going. In this case, well, sometimes if you have something that you turn on and off, like a power up, you could just short a couple of nodes and then kick it to get it started, or you might use more sort of clever startup things, but you need some way to start it up. Okay, assuming now that we have a 1 to 4 size relationship and we place the transistor into strong inversion. So we know that we have roughly a square law model. Then we can set up the equations. We know that the currents are the same, so we can set up the equations for the current. We know that the current in the number 2 here, that's 4 times larger. And then we can find the relationship between the V effectives. And we can see that if we take, well, most of these factors disappear. We're left with VF squared is equal to 4 VF2 squared. And we can take the square root of that, and we're left with VF1 equals 2 times VF2. Now we can use the relationship for GM, where GM is given by 2ID divided by VF. And we can turn that around, and we can figure out that the impedance down here is equal to 1 over GM. Now, another point I should mention is that if we now look at the fact that VF1 is equal to 2 VF2, then it must be the case that the voltage across this impedance is given by VF2, right? Because we go up 1 V effective, we go down half of V effective, or actually this VGS1, that is 2 VF, so we go up 2, we go down 1, and we're left with 1. So the voltage across this impedance is given by the V effective 2, which means that we now have the ability to make the transconductance of whatever circuit we're using this in. So if we copy the bias current and so on and use it somewhere, then we can actually make the transconductance proportional to this impedance. And that's quite useful. That can be very useful because we can get what's called a constant transconductance. There are something that's called transconductors. We briefly look at that in a couple of weeks. There are op-amps where the transconductance or the unity gain frequency of the system is given by the transconductance divided by the load capacitance. So keeping a known transconductance, which requires a current that changes with temperature, right? Because mobility changes with temperature, threshold voltage changes with temperature. Actually, threshold voltage doesn't impact this, but mobility at least does. Keeping a constant transconductance is useful. Now, there's also other tricks that we can do, and that is in switch cap filters or switch capacitor circuits, it's sometimes useful to have a current that's proportional to capacitance. And what's possible to do is start using something called switch capacitor circuits. So imagine now that instead of having just a resistor here at Z, we actually have an impedance. So we have a capacitor that's just stabilizing the voltage, but then we have a switch, we have a capacitor, and we have another switch. Now think about how this is gonna work. We are dumping the charge across the capacitor during phi 2. So the charge across this capacitor is going to be 0. Now in phi 1, we are charging the capacitor to V0. Okay? So every single clock period, we are charging the capacitor to V0. So the charge, if we look at the current flowing through this switch capacitor thing, then it's going to be given by the average, well, charge as a function of time, right? Okay, so the charge is Q, no, sorry, it's the capacitor times the voltage. And then how often it happens, well, that's related to frequency. So now we're getting a resistor, kind of like a resistor, or an average current that depends on the capacitor, the C1, and the frequency. Now, we'll go more into switch capacitor circuits in a few weeks. Anyway, if you want to look more at band gaps, I'd highly recommend for example, the bandgap. So if you go to IEEE Explore, you can find this first sub 1 volt reference, and it explains how the circuit works and so on. And if I zoom in on one of the figures, we can see that it's a similar structure to what we had before. Slightly different. Here they have drawn the op amp all the way out. So it's a good idea to look at these type of papers, because then it can tell you how to implement the circuit. And also I'd recommend the what's it called? Besad Rosavi has some really good introductions to circuits. One of them is the bandgap. So I'd recommend reading that. It gives a good introduction to the details and design. So some references. You'll find those in the lecture notes, which I'll post below the video and so on. That's it for today. Have a fantastic day.